All right, so here's section 10.2, and remember in chapter 10, we have three main ideas. We have our conics from section 1, we have parametric equations for sections 2 and 3, and then we have polar equations for sections 4, 5, and 6. So getting into parametric equations today and plane curves, a lot of little vocabulary changing and things, and we'll obviously talk about that through the lesson here. When we have a plane curve, or what we like to do, what we're going to use with parametric equations, is that 3 variables are used instead of 2. Usually we just have x and y, and that's going to represent a curve in the plane. Well, 2 variables can tell us where an object has been, which is a good thing. It's obviously we want to know where it's been, but 3 variables can tell us a little bit more. It can tell us where an object has been, and when the object was at a given point. And so that where and that when, and that parametric puts in that when for us. So to determine time, which is our when, a third variable is introduced. Well, appropriately it's t, because we want to know when, which would be a time, and that is then called our parameter. So parametric equations, by definition, we have f and g are continuous functions of t, and t is our parameter. So a parametric equation actually has 2 equations. It'll be x is equal to some function in terms of t, and y is equal to another function in terms of t. An example here is we have an object is propelled into the air at an angle of 45 degrees with an initial velocity of 48 feet per second. This equation, or this situation, is modeled by a rectangular equation. So whenever it's rectangular equation, that vocab means that we are just in terms of our x and y. So whenever you see rectangular is what we've always been dealing with. That is in terms of just x and just y. Well, if we would graph this, so I'll take out my calculator, and maybe it will turn on for me. All right, so we have when you plug that in, x has to be squared first. So we could put in negative x squared. I don't think you would need parentheses. Divided by 72. And then we want to add x to that. For our Windows settings, let's go from 0 to, let's go to 20 to start. And I have no idea how high this is going to go. So let's go from 0 to 20. We may have to increase our window settings. So if we graph this, I definitely need more x values. And I'm going to increase that to 60. And maybe just the y's. I think 20 would probably be sufficient, but we'll go 30 just to be more safe. And I know why it's not showing, because I definitely need, my Windows setting. With this 72, it's going to go to 72, so I'm just going to go to 80. And now when we graph it, that looks like if an object is propelled into the air, that's definitely the shape that it would take. So we have our nice parabola. This, remember, is our rectangular equation. And so really it can just tell us this is where an object has been. It has followed that path. So I'm just going to sketch this and put it over here. We know that we can put our x-intercept at 72. And we have the general shape. Well, with a parametric equation, remember that can tell us where an object has been and when it was at that point. So with our calculators, everybody has to have their calculator out, so you may need to pause this until everybody has their calculator. And we have to change the mode of our calculator. So right now, our mode, we've always been in this regular function mode. Well, now we want to go to that PAR for parametric. Press enter on it so that it's highlighted, and then I just quit that. And now if I want to graph, when I go to y equals, you will see that you have x sub 1, y sub 1. because a parametric equation has to have the x and the y. And then if you want to graph two parametric equations, that's fine. There's x sub 2, y sub 2, x sub 3, y sub 3, etc. So if I want to graph this now, I have 24. And when you press your variable, because it's parametric, it's going to put a t in there instead of our typical x. So 24t times the square root 2. And our y is negative 16t squared plus 24t square root 2. And now when we look at our window setting has our window, the minimum is at -1. Well, that doesn't really make a lot of sense because we're not going to look at a negative time for this if we're throwing an object or propelling an object into the air. So I'm going to stay from 0, basically that means 0 seconds, and then our maximum. And I don't know how long this is in the air, so we can, let's just go to 10 seconds. This t step is set, basically what it means is that it's going to calculate every 1/10 of a second the new position. Our x minimum, we know that basically we're going to graph the exact same thing. So now we already know that we can go from 0 to 80 and we will have our entire graph. And then our y's will go from 0 to 30. Now when we graph this, it has the exact same graph to it, it's just in parametric. Well, a couple things to note. If you go to back to your window setting, and let's just say you only graph from 0 to 2. Well, that means I'm only going from 0 to 2 seconds. So if I graph it, well, it stopped a little bit short. So this thing really isn't in the air for very long. It goes pretty quick. We can even make it, if I go to 0.5, that's all you're only giving it from 0 to 0.5. At a half a second, that's the position of it. So if we want to see the entire graph, it's best to go over because we don't care after that. So if I go 5, I'm going to be sufficient for this. And I know it's definitely graphing more here, but that doesn't really matter. So that's kind of how this stuff works. What the window setting does too is if you change your t step, and let's just put in there a 1 instead of the 1/10, what this does is it only calculates the new position every second. So it's going to make your graph really choppy. So it's like there's 1 second, and then it starts coming down. So usually I say if you have that t step at a 1/10, you're going to be okay. And then it will put a curve to it. So one more time. And there's our graph. So that's the difference between our rectangular and parametric equations, is that now I can say where and when. If I go to the table, oops, my table isn't set up. I'm going to go to start at 0, and I'm going to have it change by a 1/10 of a second, and I'm going to go down to auto. Then when I go back to table, now it tells me at time 0, my x is 0, my y is 0. But at time, like if I want to know where it is at a half a second, when the time is 0.5, my x value is 16.971, my y value. So I know the exact position when the time was a half a second. And then you can scroll down and say, okay, well, what happened at 1 second? Well, at 1 second, this was the exact position of the object at 1 second. So that's our parametric equations kind of in a nutshell. And we know that these two graphs, I can graph things rectangular and I can find an equation for parametric that will graph the exact same thing. Parametric is just a little bit more, it can give us a little bit more detail. So this next stuff in C is a lot of vocab. When we talk about a graph, that is your rectangular, because it's your set of points, just x and y. But when you have just x and y, that's your rectangular equation. So a set of points, x and y, obtained as t varies over your interval. If you have a plane curve is specifically your parametric equations and the graph. And then orientation, we'll talk about orientation a lot in the next problems, but parametric equations tell us the specific direction. And so on our graphs, we'll have to put in the direction, and then we have to graph in order of increasing t-values. So we'll put orientation here in our first example. All right, so we want to sketch the curve described by x equals t squared minus 4 and y equals t divided by 2 from -2 to 3 for our time. Oftentimes I'll have you make a table for this, and so we can make a table. And remember, now we have 3 variables instead of 2. So here we have our t, we have our x, we have our y. Well, if my t values range from -2 to 3, usually I'll just have you go in integers over that interval. So then we can say our -2, -1, 0, 1, 2, 3. And now I can figure out what is x equal to, what is y equal to, by plugging them into their individual equations. So I can figure out my x values, I square my t and subtract 4. So -2 squared is 4, subtract 4, I get 0. -1 squared is 1, subtract 4, -3. Plug in a 0, -4. And pause this and complete the rest of the table. All right, now that you have your table completed, now it's just looking at the graph. So when we graph these things, we're still graphing on our regular coordinate plane, x, y. And I know our x's, we go from 0, we go to -4, and we go to a +5. All right, so for the x-axis, I better go to a -5 and a +5. And then all my points will be covered. For my y's, I have -1 all the way to 1.5. So I'm just going to go down to -2, then up to a +2. And then plugging in my points, really now the time I just ignore, and I have 0, -1, -3, -0.5, -4, 0, -3, +0.5, 0, 1, 5, 3/2. And we connect our points in the order, as we plotted them from left to right according to our table, and that tells us our orientation. So we graph it and it looks like this. And we have to stop at the end points. Do not put arrows on the end because we're specifically only going from -2 to a +3. So the endpoints are their points, they are not arrows. And then we have to indicate orientation. And so orientation, we started off, we're going in this direction. So I go here, and 1 arrow is sufficient, but to put 2 in there isn't bad. So now we have our graph. And as you can see, obviously this isn't a function. And parametric equations are really nice because you don't always have to have a function, where if it's rectangular, this is a lot harder, and it's not as familiar to what we're used to graphing. So the other thing what's weird about parametric equations is that I can have a different parametric equation that has this exact same graph. What ends up happening is that this plane curve just ends up being graphed more quickly. So here's an equivalent graph. An equivalent graph to this is x equals 4t squared minus 4, and y is equal to t. And that would be from -1 to a positive 3/2. So if you graph this on your calculator, you would have the exact same curve as what we have here. And you could take out your calculators right now. You can pause this and take out your calculators and graph this and see that it's the exact same. So pretty basic though when you're sketching. All right, the next type of problem that we have is that if we want to eliminate the parameter, if we eliminate the parameter, remember parameter is our variable of t. Basically what you're doing then is finding a rectangular equation. And why we would want to do this is we're a lot better at graphing rectangular equations because we've seen so many rectangular equations and we're used to a lot of the graphs. Where when we have our parametric equations, we don't know what the graphs are going to look like. So let's just say we have our parametric equation. I'm going to take the one from above. So x equals t squared minus 4 and y is equal to t divided by 2. So I have a parametric equation to start. Now what I want to do is solve for t. And I can solve for t in either equation, whatever one is easiest. So here we have either equation. And I'm going to solve for t in this bottom equation because that's really easy to do. I have 2y is equivalent to t. Well, now I have to substitute this t value into the equation that I did not use. So substitute, you have to use the equation that you did not use in that step 2, which basically means I have to use the x equation. So x is equal to, instead of t, I want 2y, that's squared minus 4. And now I just want to write the rectangular equation, and with rectangular equations, we usually write those in terms of y. So if we write this in terms of y, I'm going to make it x plus 4, so I added the 4 over to the left side. That's equal to 4y squared. Divide both sides by 4. And I'm going to switch and put the y squared over on the left now. Y squared equals, let's make it x divided by 4 plus 1. And if you left it as a fraction, that's completely fine too. When I create a square root, remember we also have to create the plus or minus, and that's why we can create this now that is not a function. So y is equal to positive negative square root x divided by 4 plus 1. And we've eliminated our parameter, and we can graph this if we want to. And if you graph this, remember you have to have the positive and then you have to have the negative. You'd have to make 2 graphs if it's a rectangular equation. But pretty easy to eliminate the parameter. All right, next page. So we have sketch the curve by eliminating the parameter and adjusting the domain of the resulting rectangular equation. Adjusting our domain is a pretty big thing because here they're telling us that t, or our time, has to be greater than -1. Well, for this it makes a lot of sense because our domain would have to work for both equations. Well, we know in the x equation you cannot have a t value that's less than -1. So we have to keep that in mind that, okay, t has to be greater than -1. So if I put that into my actual equation here and look at what I have for my new domain, when I plug in a -1, I know that my x value has to be greater than 0. And so in that situation for our domain, remember domain is basically comes from your x's. So if x has to be greater than 0, that tells us that our domain x has to be greater than or equal to 0 because we can, it just has to be greater than 0 because with this in the denominator you can't divide by 0. If you had a radical that's not in the denominator, you can take the square root of 0, then it would be fine, but because this one is specifically in the denominator, can't do that. So our new domain, x, has to be greater than 0. And remember, domain, plug your t value only into x because your domain deals with your x values. All right, so now this one's a little bit uglier when we want to eliminate our parameter, just because solving for t isn't as nice. Well, if you look at between the two of them, Here in y, you have 2 t's. And that's just really not ideal if you have to solve for t. Therefore, I'm going to solve for t using the x equation. So our step number 1, solve for t. And really, either equation would work. We just have to figure out which one would be best. So solving for t, I'm going to use x is equal to 1 divided by the square root t plus 1. Well, now I'm going to, in order to get rid of the radical, I'm going to square both sides. And when you square both sides, you don't add plus or minus, only when you take the square root. So now I have x squared is equal to 1 divided by t plus 1. And now I want to solve for t. What I would do here is multiply by t plus 1. But instead of saying that times x squared, I'm going to divide by x squared as well, over to the right. So I multiplied by t plus 1, divided by the x squared. And now I know that t is equivalent to 1 divided by x squared minus 1. So that's what t is equal to. Number 2, I have to substitute it into the other equation. So 2, substitute. Therefore, y is equal to, so I've already used the x equation, so y is equal to my t value, because that's in the numerator, 1 divided by x squared minus 1. That's divided by my t value, 1 divided by x squared minus 1, and then it's plus 1, which this is just one ugly mess. So then I'm going to say y is equal to, the denominator is nice. I have 1 divided by x squared. In the numerator, what I would do is I would have to get a common denominator out of this. So to try to eliminate too many steps, I'd call the 1 x squared divided by x squared. That's equivalent to 1. And now I can say my numerator is 1 minus x squared divided by x squared. Well, instead of dividing, I can multiply by the reciprocal. And conveniently, this would have to be grouped in the numerator. Our x squared simplify out. So we went from a really nasty looking equation to something that's really nice. So I have y equals 1 minus x squared. Well, in the rectangular sense, that's really nice because I know exactly what that graph looks like. Compared to when it's a parametric, if I look at this, I have no idea what I'm graphing. And that's just, we're not used to dealing with parametric. But when I look at rectangular, I can graph that very, very easily. So if I graph y equals 1 minus x squared, here would be 1, negative 1, a positive 1, and I know my graph would look like this. It's a parabola. That 1 means I have a vertical shift of up 1 because I'm subtracting, my parabola is opening down x squared. So here it is in the rectangular sense. Remember, we had to adjust our domain. So our domain has to be greater than 0, or x is greater than 0. Well, that's really nice because then, okay, I put an open circle there, and I can erase this portion of it. The one last thing that's difficult is that when you're graphing parametric, you always have to show orientation. And we can't just assume that this is going down with the arrow here. So to graph orientation, you can plug in different times. So you always start with your time, consider it like time of 0. And I can plug in a 0, that's fine. So if I plug in a 0, if my time is 0, what is my x value? So if t is equal to 0, I'm going to graph my point. So when t is 0, my x value is 1. And when t is 0, my y value is 0. So I have the point 1, 0. Well, what happens when my time is 1? Well, when time is 1, if I plug in my 1, I get 1 divided by the square root of 2. And when I plug in my 1 into the y equation, I get 1 divided by 2. Well, I know that this is less than 1. I don't know exactly what it is for sure. That's okay. I know that it's less than 1, and here's 1/2. So if this is when time was 0, and this is when time is 1, my orientation is actually going this way. And remember, you can't have an arrow, so that would have to be, actually it's not even a dot, it just ends up being a line, or your curve, and there's just nothing at the end. We can't put an arrow. I guess it's just assumed that it continues going, or to go down, but we can't actually put an arrow down there because then you have conflicting orientation. So kind of a tough one with this, eliminating the parameter and then sketching. There's a lot of little details in there. That really, it's not too bad. All right, now our parameter does not need to represent time. Usually it does, unless we're dealing with trig functions. Then it also represents an angle, and this is pretty common as well. So for example, we want to sketch a curve represented by x equals 3 cosine theta and y equals 4 sine theta. We want this, our parameter is from 0 to 2 pi, because theta is our variable. So in our two equations, so that's our parameter. And we also want to eliminate the parameter and find our corresponding rectangular equation. Well, we could use our calculators right now and graph this. And if you do choose to use your calculator, which you'll still have to show your equation later, you have to make sure when you're graphing your trig functions that your mode is in radians. We're still obviously a parametric equation. And then we can go to adjust our x and y. So x is 3 cosine theta, and y is 4 sine theta. Our window settings, window would be from 0 to 2 pi. And again, I always just find if I leave it as a tenth, I'm good to go. Well, because I know my graph here, if I'm graphing sine and cosine, I'm going to have my graph go from I'm going to go from -5 to 5. And then I'm also going to have my y's go from -5 to 5. So for our parameter, our minimum is 0, we go to 2 pi, our step is 0.1, x minimum is -5, maximum is 5, y minimum is -5, maximum is 5. We graph it, and it looks a lot like a circle, and that's just basically because it's not our screen isn't great, I guess. It's a little distorted. But this is going to be the equation of an ellipse. So if you look on your x-axis, you go from the +3 and a -3. Your y-axis, -4 and +4. So incredibly easy to graph. So I come over here, there's my +3, -3, +4, -4. Connect my points. That's a pretty good ellipse that you got there. It also shows you orientation. So I might have, if I wasn't watching carefully, but if you just retype in one of your equations, so I'm going to type a 3 over this. And now when I graph it, it shows me the orientation. And when you're graphing these, they always graph counterclockwise. So then we can put in our arrows showing orientation. And there is our curve. We do have to find our rectangular equation, and because we know our conics so well, we could just look at this and write it from here. But there is something that we need to know. And one thing that we have to use with this is that we're going to use the idea that cosine squared of theta plus sine squared of theta is equivalent to 1 using our Pythagorean identities. Well, I can get cosine and sine by itself. So I know that x divided by 3 is equivalent to cosine theta. And I know that y divided by 4 is equal to sine theta. So if I take my cosine and square it, I obviously have to square the left side as well. So I have x squared divided by 9 plus my sine squared will give me y squared divided by 16. That's equivalent to 1. And so it's really easy to write these, and you will always end up using that Pythagorean identity. So our Pythagorean identity, we can solve for sine and cosine from our parametric equations, square them, and then looking at a graph too, we know like, okay, obviously our center's at 0, 0. And on our x-axis, horizontally we move 3 from our center. On our y-axis, so vertically, we move 4 from the center. And we know that an ellipse has to equal 1. So that's pretty nice, pretty basic to tell. If you don't have a calculator to graph it, again, you can take points and say, all right, well, what if theta is equal to 0? If theta is 0, what is my point? Well, if you plug 0 in, cosine 0 is 1 times 3 will give us 3. And sine 0 is 0 times 4 is 0. So we have to go in order from our parametric equation. So we start at, if theta is 0, we have 3, 3, 0. Then we can say, well, what if theta is pi over 2? We're increasing in order. If I plug in pi over 2, cosine pi over 2 is 0, times 3 is 0. Sine pi over 2 is 1, times 4 is 4. So I go from the point 3, 0, 3, 0 is right here, to the point 0, 4, well, 0, 4 is right here, so if you're going in that direction, that can also show us orientation compared to just using your calculator. Here's our basic equation. If you have x is equal to, you can have an h in there and a k. That will just adjust your center. So h plus a cosine theta and y equals k plus b sine theta. And theta is between 0 and 2 pi. It will always be an ellipse, and it always is traced counterclockwise. What we're going to end up doing is taking x minus h divided by a. So I'm basically solving for cosine. So x subtract h divided by a, that equals cosine theta. We'll now solve for sine. So y minus k divided by b, that equals sine of theta. Well, now if I take my cosine squared plus sine squared, and you could go the other way, addition is commutative, but cosine will usually have the x with it. Sine will have the y. So if I square both, I have x minus h, that quantity squared, divided by a squared, plus y minus k, quantity squared, divided by b squared. That will equal 1, which is the equation of an ellipse, and we can graph from there. So eliminating the parameter is an aid to curve sketching. You can use your calculator too, but it is nice. The graph alone doesn't describe the objects in motion. You need to have direction or orientation. And every time you graph these, make sure that you put your orientation with it. Your calculator, you can always watch that because your calculator will tell you the direction of it. And parametric equations, remember, tell us our position, it tells us our direction, and it tells us like the speed of it, how fast it's happening at a given time. So, yeah, that's kind of the gist of it. If we have to go the other way and make a parametric equation, so basically we want to find a set of parametric equations to represent the graph of y equals 1 minus x squared. Well, we have the one that we used above, but that isn't the only set of parametric equations. So if you look at the top of your paper at number 6, we just had that rectangular equation of y equals 1 minus x squared. So one possible parametric equation, if we go back to number 6, is here's a parametric equation that worked because this was our rectangular equation that dealt with it. Chances of me coming up with that one aren't very good. And I'll probably tell you what you have to use. So we have 2 examples. For the first example, x has to equal t. Okay, well that's really nice because if x has to be equivalent to t, there's your first of your parametric equations. Remember parametric equations, you need what is x equal to, what is y equal to. All right, well x is t. Well then, if you want to know what y is, if x is equal to t, you just plug it in. So then y is equal to 1 minus, instead of x, we know x is t squared. And that's really the simplest type, and that's pretty nice. For b, we have a different thing that we want. we're going to say that our slope which we know is our derivative at our point xy. Well, if we look at this, what is our slope equal to? And it has to be dealing with our equation. So our slope is equal to negative 2x. And this part of it in here just tells us, take your slope of your function, so which is equal to dy over dx. If I take the derivative, obviously we could create differential y with respect to x. So my slope is equal to negative 2x. Well, for a parametric equation, I have to say what is x equal to and what is y equal to. Well, now I can say, all right, if m equals negative 2x, x then has to equal m, representing our slope, divided by negative 2. Well, as soon as I have what x is equal to, now I can say, well, y is equal to, again, this goes back to our equation, y is equal to 1 minus my x value. Well, here is our x value. So if I put that in, m divided by negative 2, and I have to square it. Be really careful that you don't make this plus right away, because order of operations you have to square first. So then I can clean this up a little bit. I'm going to rewrite that x is equal to m divided by 2. And this time y is equal to 1 minus m squared divided by 4. So we know that's x, there's y, and now we're looking at things just in terms of their slope. And that's okay to have our parameter in terms of slope as well. It's not very common, but it can definitely happen. All right, so now we know what parametric equations are. We can take a rectangular equation and write it as a parametric equation. We can take a parametric equation, write it as a rectangular equation, and we know what a graph. There are a couple of interesting little unique things or type of problems that we can do with parametric equations. Our first thing is a cycloid. And a cycloid is a curve traced by a point on the circumference of a circle that rolls on a straight line. So if I have my circle, if I take this point and follow it back, it started here. Now as I go around, it will come to here. And as I keep going, it's going to keep continuously making this type of a curve. And I have a little video of it for you too. So if we look at this, here's a soup can, and here's the pin that we're going to follow. So if we play this, if we follow that pin, it creates that curve. Whoop. We'll go back and watch it one more time. So we're following that pin. There it goes. So if you'd actually follow it, it just keeps going that way. All right, go back to our notes. So that's how we create our cycloid. Our parameter will be theta. It's a measure of our circle's rotation. We always begin at our origin, so 0, 0. And that's when theta is 0, our origin will be at 0, 0. When theta is equal to pi, that will be your maximum point. And to get your maximum point, you'd have pi a, and then your y value would be 2a. A is equivalent to the radius of your circle. So I don't know why they don't like to use an r here. Usually radius we always have as an r, but they use an a for this. And then when theta is equal to 2 pi, we're back to our x-axis. So like here, theta would be pi, we're at our maximum point. At 2 pi, we're back to our x-axis. At 3 pi, we're going to be back up at our maximum point. 4 pi, back to the x-axis. So if you have the parametric equations for a cycloid are as follows. X is equal to a times theta minus sine theta. And y is equal to a times 1 minus cosine theta. And remember here, a is equivalent to the radius of your circle. And you'll have to use these for a problem or two in your homework, but they're the parametric equations. So when you see cycloid, here are the parametric equations for it. Other things that we will be using are the idea of a smooth curve. So a smooth curve, we have a curve C, it's represented by a parametric equation. So we have x equals f of t, y equals g of t. Obviously that represents a parametric equation. It's on an interval I. It's considered to be smooth if the derivative of f and the derivative of g are continuous on your interval. And there's one stipulation here. They cannot simultaneously be 0, except possibly at your endpoints. So basically we have to take and we want to figure out our derivative is continuous, and our derivatives can equal 0, they just cannot simultaneously be 0. And if they're not ever simultaneously 0, then we have a smooth curve. If it's piecewise smooth, your curve is smooth on subintervals. And oftentimes we have piecewise smooth. So for an example, use the graphing utility to graph the curve represented by the parametric equation. Indicate the direction of the curve and identify any points at which the curve is not smooth. We have a perlite cycloid. So let's start by graphing this thing. So take your calculators out. They should be in radians. Clear that stuff out. Type everything in. We have 2 theta minus 4 sine theta. And our y is going to be 2 minus 4 cosine theta. And I'm going to leave my window for now. I'll see what the graph looks like. Oh boy. Well, I didn't see very much of my graph. We're definitely going to have to make this quite a bit larger. And we only went from 0 to 2 pi, which needs to be significantly greater. So I'm going to stay at 0 and go to, let's go like 12 pi. It looked like my x values weren't quite high enough. Maybe let's go from like -8 to a +8. And then our y's definitely needed to be increased. So I'm going to stay at -5, but I'm going to go to like 15. And this might be way too big. So I hope we have everything graphed in there. I obviously did that the wrong way. Whoops. Go back to your Windows settings. Well, now this stuff up here, it has to go through my 12 pi, which is somewhere over here, which I didn't see. I don't know how I screwed up my x's and y's. Oh well. I think we can go to second off and it'll quit. Second quit. Or just take a break and wait for it. Alright, Windows settings. My t's are fine. My x's, I need to make them much bigger. So I'm going to go, I don't know, negative, we can keep it I guess at -8, and let's go to like 25. My y's, God, I think -5 to, I don't know, maybe -10 to 10. But we know we want something like a cycloid, like our last graph. This shows a little bit more. So this cycloid, because you have a perlate cycloid, it's not that exact point that it went to before, but we have this type of a curve. And really this is just going to keep repeating and keep going and going and going. Again, I could definitely want to make my Windows settings a little bit bigger here. I have to have patience for it. And just to increase that x value. If I make my y value, or my parameter, if I adjust that, instead of starting at 0, we could start at like -2 pi. And I'm going to make my x's even go to 40. So I changed my parameter, -2 pi, that's 12 pi, and now I'm going to 40. But that -2 pi will just show a little bit more over here on the, to the left. And here is our perlate cycloid. Well, to me it looks pretty smooth. It doesn't look like it ever goes to a sharp point Like on the previous page, we had a sharp point. Here, this looks really smooth to me, but we do have to check it. And obviously, there are always going to be patterns and keep repeating. So what I have to do to check to make sure that this is a smooth curve is look at the derivative. So smooth curve, it tells us that our derivatives have to be continuous, but they cannot simultaneously be 0. So the derivative of x would be 2 minus 4 cosine theta. And then usually I take this derivative, and yes, it's continuous because cosine is continuous. So I set this equal to 0. Well, then cosine of theta, where is it equal to 0? I would subtract 2, so I have a negative 2 divided by a negative 4, which gives me 1/2. Well, I know that cosine of theta is equal to a positive 1/2 in quadrants 1 and 4, and it would be at pi over 3, 60 degrees, and then 5 pi over 3. So I have a continuous derivative. Here is where my derivative is equal to 0. I have to check the same thing with y because it's a parametric equation. So my derivative now, derivative of 2 is 0. Then it would be minus 4, derivative of cosine is a negative sine, so it makes it a positive sine theta. Yes, that's a continuous function. And then where is this equal to 0? Well, it's when sine of theta equals 0. When does sine of theta equal 0? And sine of theta is equal to 0 at 0, pi, 2 pi, etc. Same thing over here. This keeps going because our domain here, our thetas go on and on. Well, we know that these two things are never going to simultaneously be 0. Therefore, this is a smooth curve. So our derivatives of each function, we know they're continuous. Where are they equal to 0? We found the the point, and not at the same time. So it's always a smooth curve. All right, a couple miscellaneous examples here. We want to sketch the curve represented by our parametric equations, indicate orientation of our curve, and write the corresponding rectangular equation by eliminating the parameter. So these things should be pretty basic. You can graph these on your calculator if you'd like to. But why don't you pause this and do these two examples on your own? All right, so now that you've paused it, and we look at our solutions here. When we solve for t, you get plus or minus. When you take it to the fourth, you know it's always going to be positive. So then you can rewrite it, and you don't have to worry about the positive or negative. And here's our rectangular equation. When you graph this, it's kind of interesting because you have your t squared, and they don't give us a domain. Sometimes they do. In this situation, there isn't a domain. So if you plug in a negative, you're graphing it, the parabola is coming down, but then when your t-value becomes positive, as you watch it, then it goes back up again. So that's kind of a unique one. Usually there's going to be a parameter with it. And then obviously for b, we know that that's going to be our ellipse. Isolate cosine and sine. Once you square them, there's your equation of your ellipse. Remember, ellipse is always graphed. Orientation is always counterclockwise. One last problem here. So you have to eliminate the parameter and obtain the standard form of a rectangular equation. If you have a hyperbola, you have x equals h plus a secant theta, and y equals k plus b tangent theta. If we look at our Pythagorean identity, we know that 1 plus tangent squared of theta equals secant squared theta. And we know that a hyperbola always has to equal 1. Therefore, 1 is equal to secant squared theta minus tangent squared theta. What we have to be conscious about is with our hyperbolas, sometimes your x is first, sometimes your y is first in your when you're graphing it. So you really have to be conscious of that and know a point or figure, like you can see down here where we have vertices. You really have to know which is going to come first, whether it's going to be your x or y. But with a hyperbola, it's always considered that x is equal to that h plus a secant theta. So x always goes with secant, and in this situation when we graphed it, secant is your first term here. But we know with hyperbolas it doesn't have to be. So we do have to be very, very conscious about that when we do our problems. And then we have y equals k plus b tangent theta, so y and k go together. But same type of situation happens. I can take x, subtract h, divided by a. That's equal to our secant theta. Just like we did with our ellipse. Y minus k divided by b. That's equal to tangent theta. If I take secant squared minus tangent squared, so if I square them, I have x minus h, that quantity squared, divided by a squared. And then I'm subtracting y minus k, that quantity squared, divided by b squared. We know that that's equivalent to 1. Going back to last section, we know that hk represents our center. A is always in our first equation here. A gives us our distance from your center to your vertex. B is not it's not really seen on the graph except for when you're graphing your asymptotes. And C, remember, you get from a squared plus b squared equals c squared, and c is the distance from your center to your foci. So last problem, use the results of A to find a set of parametric equations for our hyperbola. And I made this one kind of hard because our vertices are at 0, 1, 0, negative 1, and our foci are at 0, 2, 0, negative 2. So we know our hyperbola is going to look like this. Whoa, wrong point there. As we go around our foci, because our hyperbola is set up like this, our y value will have to come first. So if y has to come first, that will be okay. We just know that we have to have y minus k, that quantity squared. And if we look up here, it's divided by b squared. Well, I know that has to be an a, but it's okay. We're just going to take it from this portion of it that your x and y have to go together. And then you have to subtract x minus h, that quantity squared, divided by a squared, for that to equal 1. Well, in this situation, what I would do is say, I know that my a value is equivalent to 1. We have to calculate our b value, and we know that our c value, distance from your center to your foci, is 2. Therefore, a squared plus b squared equals c squared. We have 1 plus b squared equals c squared would give us 4. B squared would be 3, so b is the square root of 3. When we graph this now, our center, it's really nice because that's at 0, 0. So we don't have to worry about our hk. But then we would have, if we look back at the top up here, y is going to equal our b value, which is the square root of 3. That's tangent theta. And then x is equal to a, which is 1 secant theta. Well, maybe this isn't the greatest way to explain this, I'm not really sure, but if we take this situation, we know that we have to have secant squared minus tangent squared. And so if we follow our formulas, that's how it would look, that we need to have secant squared minus tangent squared. In order to adjust for that, if we have our hyperbola going up and down instead of opening to the left and right, these variables have to switch. So this becomes the x, and this becomes the y. And basically it's because when we set up our equations now, I need this to be, I have to follow the Pythagorean identity because subtraction isn't commutative. So secant has to be first here. And when you have your secant squared, then is your y, and tangent squared will then be your x, so then that will switch the order of it. So kind of weird if it opens up or down. And that's really if it's opening up or down instead of to the left and right, then you just have to switch the order of those two things. And you can graph it on your calculator to check to make sure this is the right parametric equation. So if it's opening the wrong way, like obviously left and right instead of up and down, all you do is switch your x and y around, and that will switch it. All right. So there's your homework assignment for your parametric equations. Good luck. Have fun.